Hi everyone, I'm Sandy Lucas. I'm the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us for this webinar series called Years of Maritime and PISTON Field Campaign. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of the prior talks in the past CVP webinars, I encourage you to view them from our website. All of the sessions have been posted, and these that are being recorded today will be posted soon. The Years of Maritime Continent is an ongoing set of international field campaigns and modeling efforts focused on the Maritime Continent region. YMC is led by the countries of Japan, Indonesia, and the US, and has partnerships with several other countries. Of particular interest to NOAA and the Climate Variability and Predictability Program is to improve understanding of processes that affect the propagation of intraseasonal oscillations, such as MJO, in the Maritime Continent and its broader regions. MJO is important to local weather and climate, as well as having global teleconnections. However, the Maritime Continent region can sometimes act as a barrier to the propagation of MJO, and weather and climate models have a hard time reproducing this effect. In response to that need, the CVP program solicited for observation and modeling projects that investigate different processes that affect the MJO. Additionally, in collaboration with research, CVP has several this year's webinar covers the 16 projects by CVP, and I look forward to hearing the results in this series. I'd like to thank Gabriella Jeliaskov, the CVP student visitor, the organizer of this for all the work she's done putting this together. Gabriella has a commitment today, so the ESSM, communication specialist and science writer, will be facilitating the webinar today. Thank you, Victoria. At this point, I'll turn it over to you for the full introduction of the series today.
All right. Thank you, Sandy. Hello, everybody, and welcome to the fourth of 10 webinar sessions on the topic of Years of Maritime Continent, which will feature 2 presentations per session and will run from September 10th, 2020 to March 11th, 2021. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned with a broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. As you listen to the presentations, if you have a question you would like to ask the presenter, please raise your hand. Raise your hand is a feature which you can find on the control panel for GoToWebinar. At the end of the presentation, I will unmute those who have raised their hands so they can ask their questions using their audio. If you have audio problems, I will ask that you type your question in the questions box, which can also be found on your control panel. Our first speaker today is Dr. Jiaosha Pu from the University of Utah. Jiaosha is a professor in the Department of Atmospheric Sciences. Her primary research interests are atmospheric data assimilation, numerical modeling, and predictability. To date, Jiaosha has authored over 100 peer-reviewed journal articles and participated in many major field programs. She has also served as a member of both national and international science teams and review panels. Jiaosha received an Outstanding Faculty Teaching Award from the College of Mines and Earth Sciences at the University of Utah in 2012. She is also a Fellow of the American Meteorological Society and the Royal Meteorological Society. Jiaosha, thank you so much for joining us. At this time, we will turn the controls over to you.
Okay, good afternoon, everyone. My topic today is talk about the diurnal cycle of wind and precipitation over the maritime continental under MJO influence. Specifically, I will give some perspectives from the cloud permitting simulation and the data simulation. First of all, I would like to acknowledge my postdoc and the students for this work, and also my collaborator, Dr. Qidong Zhang from NOAA, and Courtney Schumacher from Texas A&M University, and also Agi from Indonesia. So first question is just give a background of why the cloud permitting scale is needed for the study of the maritime continental region weather and climate. So as we all know, atmospheric convection in the maritime continental region undergoes substantial multi-scale variability on the diurnal, synoptical, interseason, and seasonal scales. So as you can see an example of the Australia in the Cape York Peninsula here. So in this slide here, so the figure here showing you the evolution of the precipitation from eye merge, and you can see in the typical day of the weekly constraint, you can see in this how the convection initiate and experience this upscale growth and propagating in the region. So as for this typical case in the weak synoptical forcing, so we expect this event driven by the land sea breeze and also thermally driven the convergence over the land. So they're both influencing the region. So as you can see here in the right side, the panel showing you the WRF cloud permitting simulation in the upper panel. So you can clearly see the evolution of the local convergence and the land sea breeze. However, in the meantime, so if you look at the ER5 field, so you cannot see this land sea breeze feature, and it's all missed in this large scale analysis. So the significant question here is available global analysis and the reanalysis product cannot accurately represent detailed feature of convective system over the maritime continental. Because of the causal resolution and also the deficiency in the cumulus parameterization scheme. So therefore, as an ultimate objective of our study, so we want to enhance the understanding of interaction between small-scale convective system and the MGO. And so our approach to take is to do the data simulation and high-resolution numeric simulation at cloud permitting scale using mesoscale weather research and forecasting model. So we intended to produce hourly 3-kilometer horizontal resolution analysis for some of the YMC intense observation periods. So as expected, so this two diagram shows you the observations we can expect from the YMC campaign during this 2-year period. So the next panel showing you the radar sites, so we can see this very dense radar network, and the right sides we can see in some of the dense radial sun, and also the intensive observation area. So even we set the goal to do the data simulation with dense observations, but up to now we did not really get access to the most of the data. But we did our best to conduct some of the study to demonstrate what we can do with this cloud permitting scale simulation and the data simulation. So the approach we took is, here is our model domain we set for the regional simulation. So we have 3 level nested domain for WRF model, and the finest one is 3 kilometer, which is cloud permitting scale. And we emphasized in the 2 study period, one is January and February 2018, and the other one is July, August 2017. And during these 2 periods, we see the MGO propagating in the maritime continental. And we did 3 sets of the study. Now, one is the code star, so we use this numeric weather prediction model, GFS, NCEP global model, to initialize and also give the boundary condition of the WRF model. We produce this 3 months long simulation for these 2 MGO events. So this is the first thing we have done. The other things we did the data simulation at cloud permitting scale, and they use all the NCEP operationally available satellite and the conventional data over the Maritime continental and did the data simulation for the 6-hourly analysis over the January 2018, just to see how much we can gain from the data simulation in terms of the cloud permitting scale simulation. And then lastly, we also did a radar data simulation for the local area, particularly in the PISTON station over the West Sumatra. We used the 3D wire data simulation method and also this hybrid 3D variational and ensemble data simulation method to do radar data simulation. So in rest of the talk, I will just spread for different topics and showing you some of the results and what we learned from our simulation and the data simulation. So first of all, I'd like to show you the results about the diurnal cycle of precipitation under the MJO influence during the January and February 2018. And this result has been published in the JGR this year. If you want to see the detail, you can check, but I give a quick summary here. And so basically, we did this 2 months cold start simulation with the WRF. And as you can see, during these 2 months, this figure in the right showing you the large scale condition and the convection and also the circulation over the region. So as you can see, in these 2 months, we see the MJO propagating, and we emphasize on the 3 notable islands in the region. So Sumatra as a steep terrain, and Borneo as a flat terrain region, and New Guinea as typical this mountain and the valley region. So as you can see, so during this time period for these 3 islands, so they experience different MJO phases in the different time. And we want to examine to see the variability, not only spatially, but also time variability, and how this diurnal precipitation depend on the MJO phase. So first things, let's check how this cloud permitting scale simulation performed. So here in the left panel, we compared the WRF simulation with the iMerge and the CMOS satellite-derived precipitation. So this hormonal diagram showing you the January to February 2018, the 3-hourly precipitation averaged over this tropical region around the equator. So you can see this WRF model has well simulated the precipitation evolution over the region and also captured the major feature during the MJO period. As for the diurnal cycle of the precipitation, we compared the WRF simulation with satellite retrievers in the right state of the panel here. So we compared this averaged amplitude of the diurnal cycle of the precipitation and also the peak time, so which is represented as phase of this diurnal cycle. So you can see in the WRF model well captured all the major features, while at the same time the WRF simulation overestimates the rainfall and also has the early start of the peak time. So it's pretty slightly aggressive than the real life, but it's still very good. So then we move to the comparator in a different region. So first of all, we're showing here the characterizes diurnal cycle or the steep topograph use this Sumatra as an example. So as you can see here, we demonstrated here both satellite and WRF model simulate the mean diurnal cycle of precipitation over the Sumatra region. So you can see in this here, so the satellite and the WRF showing the agreed major feature. And so in terms of the different MJO phase, you can see in the variability, which indicates the MGO modulates the amplitude, the time, and the propagating of the Dano cycle of the precipitation. So specifically, if you compare this MGO convective phase and the suppressed field, suppressed phase, so you can see that the local suppressed condition are generally responsible for enhanced and early trigger of the Dano cycle of the precipitation over land, and the strong and the further offshore propagating over the region. So the opposite is true on the local active condition. So there are strong contrasting between the active and the suppressed phase, and the suppressed phase give more active and early triggering of the convection. So we also looked at the details about this land sea breeze, mountain valley breeze, and also the gravity wave triggering in the around the Sumatra region. So as you can see in here, so left set of the panel showing you this land sea breeze activity, and the right panel showing you this gravity wave activity. You can see in the MGO suppressed phase makes the land sea breeze and the gravity wave are well developed with early occurrence and a strong amplitude. In the meantime, the convective phase, you can see in the land sea breeze are weak, and so with later occurrence, the differences between these two phases in terms of the occurrence time of the Dano cycle is about 2 to 3 hours. It's very notable. And both sea breeze front and the valley breeze trigger the convection over the peak terrain of the Sumatra. So this is the steep terrain case. And so then we look the flat terrain case over the Borneo. And as you can see in here, you will see over this flat terrain island. So the inter-seasonal variability of the Dano cycle of precipitation is very weak. You can see how similar these figures are, especially from the convective phase and the suppressed phase in the left, and also in the right set of the figure. You can see how similar they are. So which means for the flat island, the penetration of the sea breeze fronts trigger convection over the coastline, and this is true for many cases. So the implication here compared with the Sumatra case is the steep extent of the topography may significantly influence the MGO modulation effect on the Dano cycle of precipitation over the Maritime continental region. To prove this, we conducted the sensitivity study over the New Guinea area. As I mentioned, this New Guinea area gives a nice configuration of the topography in terms of the high mountain, which is in the middle, and also flat terrain in the both sides, and also land sea contrast, which is much clearer and ideal for this type of the study. And we did the control simulation, which used the real terrain, and also the one we removed the terrain, which means without the topography in this region. And so we conducted a study. What we found is the convective triggering time will be delayed about 3 hours if we don't have this topography. So which means the topography itself plays a significant role in triggering the convection. And in the meantime, in terms of the convective initiation location, for the with the terrain, it's peak in the mountain, and but without the terrain, it will be in the plain area near the coastline. Another thing differences is the triggering convection triggering mechanism are different. So in the control simulation with the terrain, we see the valley breeze convergence plays a bigger role, but without the topography, the penetration of sea breeze fronts will be the major reason which trigger the convection. So this is something we find out with this cloud permitting scale simulation, because it gives all kinds of details. And then we move to another thing in July-August 2017 cases, and to see how the MGO relate the moisture variation with the cloud effects, because one of the advantages of this cloud permitting scale simulation is it offers a detailed cloud structure. So then in this event, so as shown here, so we see in this MGO propagating during this period, and so especially so we use the model simulation to capture this major rainfall feature, and also MGO eastward propagation triggered from the eastern Maritime continental over the Sulawesi Sea. So then our study will be emphasize on this Sulawesi Sea region, so which is marked as this two solid line on the left panel. So you can see this is a narrow region, but it is good region to study. So first thing is we looked at this evolution of the specific humidity and the precipitation, and also the vertical velocity over this MGO period. So what we found here is in the preconditioning period, you see the normal distribution. So the moisture is more on the lower level, and so upper level is drying. But during this MGO active convective phase, you can see in this moisture advection, so this vertically, and so you have the charge of the moisture, and also with the evolution of this MGO, so it's decaying, and then so in this suppressed period, it has a very dry area. So then this is well corresponding with the vertical velocity and also the precipitation activity. So this is just to characterize this whole moisture evolution. And the discharge of the moisture immediately after this MGO deep convection was determined only by the horizontal moisture advection. So this is found with a more large-scale moisture budget study. So we did this detail, just examine this evolution of this moisture during this MGO period. And with this cloud permitting scale simulation, we also able to do this cloud classification and also study this column process. So the major conclusion is here. So the area average of deep convective, deep stratiform and shallow convective clouds reach the peak during the peak stage of MGO precipitation, and the elevated stratiform cloud reach a peak during the cloud decaying phase. So this is about the cloud. And then another thing regarding to the column process is vertical advection due to the upward motion was induced by the combination of a decreased elevated stratiform cloud and greenhouse warm effects from increased deep convective and stratiform clouds. So it caused a moistening effect throughout the column. So we did this diagnosis, but we still tuning our simulation during the period, and also further calibrate these results. And we submit this part of the results to the GS, and we got some nice review back, and we have additional work to do, and this will worth a lot of discussion in the future. So the previous, what I shown you is all the about the simulation. So then now move to the data simulation. So as I said, at this point we did not get this dense and this enhanced observation from the YMC campaign. So then we move to assimilate this conventional data, but use very high resolution instead of the coastal resolution in the region. And So just showing you an example. So we got nice coverage of satellite readings over the region, and also this Cygnus is one of NASA new satellite, which is measures the ocean surface wind. We thought this is not only the good data sets for the ocean surface wind, but also they carry significant signal for the LC fraction. So we are assimilating this data into work model, and we conducted 6-hourly analysis cycle over the region. We examined what's the data assimilation impact. So first thing is we verified whether this analysis is good. So we compared this RMSE fit of the analysis to the sounding observation and compare with the ER5 analysis and also the experimental results, the data simulation. So basically in the next panel here, you can see clearly these data simulation results showing in the green and the blue much better than the ERA5 or WRF simulation without data simulation. So if we check the monthly average precipitation, so you can see in this data simulation certainly mitigating this overestimated rainfall over the region. So which is something good we expected. And also we did this UF spatial model of no-pass filter for the hourly mean precipitation over the region. So as you can see how much this US first two major component can explain the precipitation structure. But most notably here is this principal component represent here from the different experiment. So this PC1 mainly represents this diurnal variation over the ocean, and this PC2 is over land. So you can see I noted in the early presentation, so the WRF model has given very aggressive diurnal cycle, which means the peak time or transition time starts much earlier than the observed time. So you can see in here, this black line represents this aggressive performance. So, but with the data assimilation, you can see how much correction we can get. So here we gain almost like 2 hour or 1 hour correction in terms of this transition time. So then this gives us a confidence about this regional data assimilation. So we are working on further diagnose all these results with other detailed study. But at least, so this is quite promising. And then last one is we did the radar data simulation. So this one we done with the regional study. This radar is come from the PISTON station, which in the west coast of the Sumatra. So we use the same resolution but smaller domain because this is we only have radar from one station, which is here. And so as you can see in here, so this is we compare the daily 2-meter temperature evolution and also precipitation average. So you can see in the with the radar data simulation, we can well correct some of the error over the region in terms of this diurnal variation of the temperature, especially for the precipitation. You can see in here, so this red is I merge, and so this green is with data assimilation, blue is without data assimilation. You can see how much we can correct the diurnal variation of precipitation over this strait or this mountain region. So for the mountain region, it seems quite significant here. And one other notable point here is this figure showing you the comparison data assimilation results with the I merge for the two cases. So the one case is under strong MGO influence, another one is under the weak MGO influence. So you can see in here, so in both cases, you can see how much we can improve this precipitation evolution in the offshore and also the mountain region close by this coastline of Sumatra. So the notable thing is under the weak MGO influence, the radar data simulation plays more significant role in the local analysis and forecast. Why in the in this strong constraint case, so we see less influence from the radar data simulation, although it is positive impact. So this indicates that more data are needed to represent the MGO influence from the large scale perspectives. So this is something we want to make note and call for attention for the community to provide more data for this study. Okay, just to give a concluding remark. So as you can see, so the work numeric simulation at cloud permitting scale, especially this with data simulation, can represent significant feature of the dynamic evolution of wind and precipitation during MGO events. So therefore, so those cloud permitting simulation and data simulation can facilitate the process study to characterize and understand the multi-scale interaction over the region. So our ongoing work certainly is to understand these processes with a detailed analysis as we did for the first case. And also we are currently working on the comprehensive study to understand the land sea breeze and their role in the convection, triggering upscale growth and propagating, as well as the interaction with MGO. Certainly, we wish to do the more comprehensive evaluation with data simulation, because I have already demonstrated how useful data simulation could be in the process study over this region. So lastly, I would like to continue collaboration with YMC and the PISTON community, because I know many of you have this data, and so if you like to share your data with me, and just contact me, and so we can have some collaboration and collaborative research. Okay, so this is all I have. Thank you very much for your attention.
All right, thank you so much, Joshua. I think we have time for maybe one question, and I see that Mike Patterson is raising his hand.
Thank you. Nice talk, Tajia. The question I have, so as this is a process study focused effort, I do have a question regarding the implications for operational prediction. So in terms of, can you say something about the eventual need for cloud permitting modeling capability to capture diurnal variability, topography influences, deep and shallow convection interactions in order to enable prediction of the propagation of the MJO across the maritime continent? Is this pointing to us needing modeling at that scale in order to capture the key features that participate in the propagation?
Okay, I would say this is a great question, and also this is a bigger point of view we should share. I think in our currently, especially with ECMWF and NCEP efforts, so they are moving on unified model. So in the future, with this cloud permitting scale, weather and climate model. So then in the future, I think this this cloud permitting scale simulation would help this forecasting efforts, and we have many of the work needs to be done. So the improve these physics processes and the initial conditions, and also understand the physics processes of the phenomena. So I think this is the way to move.
If I can, just an addendum to that question regarding the observations then as well. So do you also foresee the need for higher resolution observational data sets for the purposes of prediction?
Okay, this is another good question. I think in general, these high resolution data sets are needed, but in the meantime, so because they are very expensive, so then I think in the future, that's why we need to do the process study to understand so which variable are more essential to the prediction. So then we can take the just economy way to do the observation to take the best and the most useful data we can. That's the one way. Another way is some of the things called the targeting observation or adaptive observation, and which helps best to utilize the data we currently have, especially the satellite data. We can so move in that direction.
Terrific. Thank you so much.
Thank you.
All right, Jiaxia, again, thank you so much for your presentation today.
Thank you.
With that, we are going to switch to our next presenter. Up next is a presentation by Dr. Sean Johnston from the Scripps Institution of Oceanography. Sean is an associate researcher at Scripps and studies internal waves and upper ocean processes with ship-based measurements and autonomous platforms. His undergraduate degree is in engineering physics from Queen's University in Kingston, Canada. He obtained his PhD from the University of Hawaii. Sean, thank you so much for joining us today. At this time, I'm going to switch the controls over to you.
Okay, great. All right, so I'll be talking on some measurements we made in advance of Super Typhoon Mangkhut in the Western Pacific. Here's the Philippines. This grayscale is the sea surface temperature following the wake of Super Typhoon Mangkhut here, shown in the circles. And these are the trajectories of our 8 floats as they were advected westward in the North Equatorial Current. And this plot here shows you an example of a temperature section down to 50 meters, floats profile to 200 meters over 2 months from roughly early September into the end of October. And as I said, the floats profiled deeper, and so we were also able to look at the near inertial oscillations in the wake. And this work was funded by NOAA, obviously, and we received a lot of help from all our PISTON colleagues here. Noel's a grad student at Scripps, and he's authored one of the papers I'm going to talk about today. There we go. All right, so if there's a theme to this talk, it's the indirect influence of the subsurface structure on SST. As we all know, tropical cyclones weaken over cold SST. We saw a wake which had very weak subsurface stratification. The subsurface temperature can remain cool for weeks after a tropical cyclone, even if the SST warms. And then this cold, weakly stratified wake can later indirectly contribute to the air-sea fluxes under a subsequent tropical cyclone by its effects on SST. We also saw generation of lots of near inertial waves, very large ones. The near inertial current shear then leads to mixing, which brings cold water upward that again affects the tropical cyclones. And we also observed how these near inertial waves propagated vertically out of the mixed layer. So if there's less near inertial energy in the mixed layer and it's removed from the mixed layer, then maybe you have less energy available for mixing. So that is an important indirect effect as well. And lastly, I'd just like to point out one previous paper in particular, which showed that when you include winds and stratification in three-day forecasts of tropical cyclones in the West Pacific, you can explain up to 32% of the variance in cyclone intensification. But if you only include winds or SST or depth mean temperature, then you explain a factor of 2 to 3 less variance. So this again points out the importance of subsurface structure. So we have 3 papers in various stages of completion. The first one showed, and I'm going to touch on all 3 in 3 parts of this talk very briefly. So the first one showed advection by the North Equatorial Current of the wake of Super Typhoon Mangkhut, and that this weakly stratified wake possibly affected a subsequent tropical cyclone. We'll look at a new simple model of near inertial wave generation where this is the paper authored by Noel, our grad student at Scripps. The cyclone imparts vorticity to the ocean, and then over time, because of rotation, this evolves into divergence, and the divergence moves the thermocline up and down and generates near inertial waves. And lastly, we'll look at how near inertial energy propagates vertically out of the mixed layer, and this is due to the wakes, mesoscale vorticity, and mesoscale current shear. All right, here's a little movie. We'll see how the floats were deployed here at about 1:35 east. And then we'll see a sequence of 3 typhoons come by very quickly. That's Mangkhut. And there's about a week of separation. Trami comes by, and then another week we see Kongray come by. The ocean cools quite a bit, and this cooling persists for almost 2 months until the last typhoon Yutu came by, and we just saw it weaken over the wake, just a little bit right there, and we'll get back to that later. And then you can see the tracks of the floats. They move slowly across the Western Pacific with the North Equatorial Current. So our floats are solo 2s. They're profiling floats that go from the surface down to 200 meters. They're the same floats that are used in Argo, except we're cycling them very quickly from the surface down to 200 meters every 40 minutes. They each lasted about, 2 months in total. We also get one other piece of data we get that has proved valuable is the depth mean velocity over their profiling range. And this comes from GPS position differences from the start of the profile to the end of the profile. And also we get the surface velocity over a shorter interval between the end of one dive and the start of the next dive. And as I briefly mentioned at the start, these floats were all deployed with the cooperation of ONR's PISTON program from the Thompson. They were deployed in front of Super Typhoon Mangkhut and measured varying distances and from the cyclone, and also experienced varying winds. So part 1, the NEC advects the cold wake. So here's the SST snapshot of Mangkhut, just as it was making landfall at the Philippines. The floats were over here. Here's the cold wake. And then 2 months, or well, month and a half later, Super Typhoon Yutu comes by. It weakens over this bit of the cold wake here, and then continues on into the Philippines. And so what I'm going to suggest is that Yutu weakened over the cold wake, and this cold wake was advected westward, which we can see in the satellite data. So we're going to take 2 zonal slices here, and look at the Hofmüller diagrams. This is the northern line. This is the longitudinal position of the typhoons, although they were at different latitudes. So there's Mangkhut coming by very quickly, Trami similar speed, and then it went back east. Kongray also came across here. See strong cold wake. And then you see this cold wake advected on the slow line, which is the North Equatorial Current. And when Yutu comes by, we see weakening and the strongest cold wake where these lines intersect, which suggests that the wake is being advected. So on the southern line over in this panel is closer to the floats. This is the cold wake produced by Super Typhoon Mangkhut. And as if we follow along a similar characteristic at, for the North Equatorial Current, this corresponds to roughly a 20 centimeter per second westward drift. You see the strong cold wakes generally occur where this original cold wake intersects the propagation of the subsequent typhoons. The water warms. Again, this is about 1 month later, we see the strongest cold wake again, where the 2 characteristics from the typhoon and the NEC intersect. So turning now to the float data, these are the 3 floats closest to the typhoon. The pink one and the red one went right under the eye of Super Typhoon Mangkhut. And you can see large near inertial oscillations here with a 2-day period. The water cooled substantially, and then diurnal warming. You can see some nice diurnal warming in the wake of all the typhoons. Oh, and then just point out here, this red float progressed all the way westward across the Pacific and would have been right under the eye of U2 as it arrived near the Philippines. And you can see here about a ½ degree cooling in advance of U2. And this float coincidentally ran out of power just before U2 passed. And I think the cooling would have been much greater had it survived. So turning to look at heat content of the upper ocean. This is the integral of the temperature anomaly from this period. And what we see is that under Mangkhut, the heat content decreased drastically, remained low for the next 2 super typhoons, and recovered slightly before U2. And so this is a typical measure used with hurricane forecasting. We're going to look at another metric, available potential energy. This is the energy required to go from the initial stratified water column at certain depths, 75, 125 meters, and then we calculate the energy required to mix to a homogeneous water column at these depths, 75, 100, 125 meters. And this is for the red float that was right in the advance of U2. And so we see at 75 meters, the energy, the available potential energy decreases drastically after Mangkhut and then after Kongray and is near 0, which means that the water column is fully mixed to 75 meters. At 100 meters after Kongray brings the APE down to something like 5 kilojoules per meter squared, and we can see these oscillations right under Mangkhut are many times that. So it seems likely that this the water column will be mixed down to 100 meters, no trouble. And then at 125 meters, we see after Trami, the available potential energy is somewhere below 20, and we can see oscillations here of 10 to 15 kilojoules per meter squared. So it seems possible that mixing will happen to 125 meters. So if we do get mixing to 100 or 125 meters, this corresponds to a temperature decrease of ½ degree to 1 degree Celsius under U2, which is similar to what I pointed out with the floats, and also similar to what we see in the satellite data. U2 weakened at this point, or just prior to this point. And so this shows coincidence, but not causation. There are many factors affecting cyclone intensification. But what is interesting is that by having an array of floats, we're able to track this cold wave for over 1,000 kilometers across the Pacific as the float array drifted in the NEC. All right, so moving along here quickly. Near inertial wave generation under a tropical cyclone. This is the track of Mangkhut again. We take roughly 2 days or inertial period of data from each of the floats shown here in the color. And we map that into a cyclone following coordinate system. So this is a long track distance. Here's 0, 0. So this is the location of the cyclone. And here we are behind the cyclone in this area, and this is ahead of the cyclone. There's cyclonic circulation in the surface current. We can calculate vorticity in colors here and divergence in the contours. And what we see is the cyclonic vorticity evolves into divergence and back to positive vorticity. And so Noel came up with a simple rearrangement of the momentum equations where we can see that vorticity evolves into divergence after the the TC. And this is just simply a damped harmonic oscillator. And so if we take a look now along the cross-track distance equals 0 slice, here's the wind forcing. This is time equals 0 and about 1 inertial period after the cyclone. You see the initial generation of vorticity, which then behaves like a damped oscillator, and similarly for divergence. And then this model predicts the upwelling pretty close to what we observe. But because it's so damped, we just go back, just because it's so damped here, it doesn't get the near inertial oscillation so well, but it certainly does remarkably well here, comparing the vorticity and divergence. All right, last part, again, very briefly. A moment to move back to our original picture. We saw the oscillations in temperature. We can convert these, band pass these, and convert the density fluctuations into velocity fluctuations. So now we can describe the velocity and density of a near inertial wave. And once we have those two components, we can calculate energy propagation for the wave. And what's interesting is that we see faster near inertial wave propagation in the wake. And there's a bunch of reasons for that. One is if there's vorticity in the wake near inertial waves are generated at a higher frequency. And so if they make it into water without that vorticity, they will propagate faster. The dispersion relation is also altered amidst mesoscale shear from the wake, and so that will also have the waves propagate faster. And if you generate if the waves become shorter wavelength, they will also propagate faster. So these are various ways to move the energy out of the mix layer. So if we go back, if we take a vertical derivative of the density fluctuations of the near inertial wave, these correspond to 25-meter displacements, which is huge for near inertial waves. Take the vertical derivative, it highlights the vertical propagation much better. And so what we see is that phase is downward in the upper ocean and group velocity is upward. Phase is upward in the interior, which means group velocity is downward. So between these pink contours, there's an interfacial wave, and it's generating topography at the mixed layer base. And so as the NEC flows over this topography, you're generating these shorter waves, it appears, and the wavelengths work out well for that. The other thing you can do to examine near inertial wave propagation is use the array as a whole. And so we do a harmonic fit to all 4 floats. This is sort of like a directional wave spectrum. You have different directions, but instead of frequency going outward, we have wavelength. So you fit to each direction at a certain wavelength, and you just go around the circle. So it's not excluded. It's not, how do I say? It's not a, you're not excluding this variance when you fit over here, for example. So anyhow, we identify the spot where it's maximum, and so this indicates a wave of roughly 500 kilometers propagating southward, where the displacements are roughly equal to a joule per meter cubed. We do this over a 4-day window. This is for the float array as a whole. And if we zoom in at a slightly smaller wavelength, we identify the interfacial wave here. This was the one I was pointing out earlier that has a shorter wavelength, 75 kilometers, and it's propagating westward, which has the near inertial wave oppositely directed to the NEC sometimes, so you get the contraction and dilation of the wave. But here's our southward main wave, westward small wave, and if you repeat these fits over various time windows, you can generate a time series of the near inertial wave amplitude and direction here, both for the mean velocity over the profiling range and also from the density fluctuations of the wave. You can calculate the total energy density of the wave, and using the dispersion relation, you can also calculate the vertical energy flux and other properties of the internal waves as well. So that was very quickly 3 different parts. Our plans, we hope to assimilate this float data into TC coamps. These are float data. This is a preliminary comparison to coamps. We see much more of the energy is propagating deeper in the float data, whereas in coamps, the near inertial energy is constrained much more in the mixed layer. So that might have implications for the typhoon, or for cooling under the typhoon later. The original purpose of our proposal was to examine diurnal warming, but then 4 typhoons passed by, PISTON was relocated from its original area, but nevertheless, we see some very substantial diurnal warming after the first 3 typhoons, so we're going to take a look at that. And lastly, in cooperation with OSU, we have floats with microstructure on them, so we could at some point hopefully measure directly measure mixing under typhoons, which would be a substantial advance. All right, that's it. Thanks.
All right, thank you so much, Sean. So at this time, we can take a few questions. If anyone would like to raise their hand and or type a question in the chat. All right, I see that Mike Patterson has his hand raised.
Thanks. Hi, Sean. Nice talk. A couple of questions actually come to mind. The one is, so in terms of downward propagation and reemergence of I guess these cold pulses, is this over days, or is there persistence over the season? I'm trying to get a feel for, and is this specific to the Pacific Basin, or should we expect to see these kinds of relationships in the other basins with their tropical cyclone passages as well?
So for the this near inertial waves, or are you talking more the advection of the wake? Sorry.
Oh yeah, so maybe not so much the inertial waves, but in terms of the, I guess what I call a cold anomaly, and the subduction of a cold anomaly, and its reemergence to impact the SST.
Right. Having trouble going back, but I think the interesting thing there is the the typhoons were in the same direction as the current, and so I think that was kind of a lucky coincidence in that you're moving the wake in the same direction as the typhoon, and that kind of reinforces it. And then also, I think we saw with the Kongray and Trami, they were going generally westward, but then went northward, but their wake still continued westward. And so, you know, the wake is moving in the direction of the current, I guess, is just a simple thing to say.
Right.
Not sure if that quite answers your.
Well, and so that leads to a second part of my question, and that is there a practical application of this high frequency sampling to tropical cyclones, say in the Atlantic Basin or in the Gulf? We've had a number of storms that have kind of taken similar tracks through the Gulf this year. Would this be a useful application there for synoptic forecasting?
I think so. I mean, this is what Steve Jane is doing. He has air-launched floats, and they, I believe, go to 400 meters. So it's not really that different. And they're generating near inertial waves, which are the main thing that is doing the mixing to cool the wake in most cases of cyclones. So I think it would be fantastic to measure more at these high frequencies. Yes.
Great. Thanks.
Plus, it would be fantastic to measure the mixing, which is still a finer measurement still. That's where we are.
All right. And I think with that, we're going to thank both Sean and Joshua again. Thank you so much both for presenting. And we would like to thank all of you for joining us for this set of presentations in our series on Years of Maritime Continent. I'd like again to thank today's presenters for taking the time to share their work with us. The recording of today's webinar will be available within the next week on our website at cpo.noaa.gov/CVP. We hope you will join us for the next webinar on November 5th. Thank you all.